I want to thank Arthur for inviting me back to Singapore. It's always a pleasure to be here and a privilege to come to NUS and talk to the brilliant minds who have assembled here. I'm going to be giving a talk in which I really want to tell a story about where I think computing is going, say, over the next 10 years or so. The story is not going to include very much at all about quantum computing per se, but what I hope that you get out of the presentation is the incredible importance of the work that's going on here because of the fact that we are literally in a transition phase within computing in general, and we've almost entered the dark continent or terra incognita. We know that there is an age that has come to an end, essentially. We have a few ideas for how to get the next few steps down the line, but we're really going to need something that is going to be able to propel the technology for computing far, far beyond where it is today. And so that's really what I'm going to try to get across to you. All right. So I'll discuss what the problem is that the industry, and I will claim rather pompously that society faces because of issues with where computing is. I'll talk a little bit about what is the opportunity. Yes, I actually have been involved in several issues with respect to starting up major programs in governments. And so I'll tell you about the latest one that I've just started up in the United States, which is a U.S. National Grand Challenge on Future Computing. So I'll talk about that a little bit. And then what I'm going to actually do is I'm going to say that what we're working on, what I'm working on personally, is not quantum computing, at least not yet. I'm still watching it. But what I am trying to do is translate things that we have been learning about the human brain into a computational system, not to build a brain or not to reproduce a brain, but just to borrow some aspects of computation that brains perform in order to allow us to make better computational systems. So before anyone gets all excited or all worried about this, I have no intention of ever building a sentient computer. And in fact, given what I know now about brains, I don't think it will be done by anyone in the next 100 years. But there are a lot of things that brains do very efficiently that I would like to be able to emulate. So I'll talk about that. I'll also mention that there is a very, very good program that I have a tremendous amount of admiration for going on in this area, and this is the Chinese Brain-Inspired Computing Research Program at Tsinghua University in Beijing. I personally think this is the best program in the world currently in this area. And I'd like to emulate it in some fashion. So I'll talk about how a brain-inspired computer is different from the von Neumann architecture that we've essentially had for the past 70 years. And I'll talk about a possible path forward, some of the things that we're investigating. So, computing. This has been absolutely the most successful technology in human history. Since the construction of the first electronic computers, Colossus in England and ENIAC in the United States, the energy cost of a particular computation has decreased by 12 orders of magnitude over a 60-year period. So in other words, every decade, the amount of energy required to perform a particular computation has decreased by a factor of 100. That is absolutely astounding. And I will claim that it is actually something that has enabled and allowed the world's economy to be able to grow and expand and keep up with population expansion. And if we hadn't had this technological capability, our current state of both technology and society would be vastly different from what it is today. So computing, really, if you look at it, what it's been doing over the past 70 years or so, it's been sort of keeping up or just a little bit ahead of sort of the two trends together. One is the growth in gross domestic product of the world, and the other one is population increase. And literally, if you just sort of think about it, it just sort of makes sense. We've been driven to build better and better computers, and why? Well, the why is because there's been more and more things that people are willing to spend money to compute. But those computations have generally been linked or tied to the way in which business was done in the last century and the way in which the population grew in the last century. And what I'm going to claim is that we're now undergoing a phase change in computing, and that the need for computation and the type of computation that we're doing is changing radically, literally right now. But this is creating a major crisis in the computing industry. And that is because there is this thing called Moore's Law, which has been the fact that the number of transistors that can be manufactured onto a particular area on a chip has been doubling for the past, well, since the 1960s anyway. It's been doubling every 18 months or so. So Moore's Law is finally coming to an end. There have been many predictions in the past that this is going to happen, and those predictions proved false because they always assumed a technological barrier. Well, now we're facing a physics barrier, the fact that the size of a transistor on a circuit is getting so small that there's literally only a few atoms wide in terms of the device itself. And after that, the device literally no longer starts to behave. It starts to become instead of something that can perform computing, it just starts fluctuating randomly. So right now, today, the industry is shipping chips in which the transistors have a minimum feature size of 14 nanometers on the chip. 14 nanometers. I mean, when I first started working in this area, 30 years ago, I never would have thought that we'd get down to this low. But in fact, it's a certainty that we will get down to 5. So, and that will happen by the end of this decade. So by roughly the year 2020 or 2021, we will have reached, as an industry, the 5 nanometer node. We'll be making transistors with minimum feature sizes of 5 nanometers, or about 15 atoms wide in terms of a feature size. But that's it. That essentially has created a feeling of, I'll just say, panic, if you want to get to it that way, among computer companies, because in fact, Moore's Law has been going on for 50 years now, and it has become an expectation. People who buy computers expect that for the same price, they're going to be able to get something that's far more capable in the future. And I would say that the industry that I work in is dependent upon this, and society has become dependent upon this as well because of the way in which things are going. And so, in roughly 5 more years, all of that comes to a crashing halt. But in fact, it's even worse than that, because there's a dirty little secret within the chip industry and the computer industry, and that is that functionally, Moore's Law actually ended 5 years ago. We can still put more and more transistors onto a chip, but the truth is that we don't turn them all on. We can't, because if we did try to turn them all on, the power dissipation would be so large, you'd vaporize the chip. So there's this thing called dark silicon. So we are making more and more transistors. We're putting more and more stuff on the chip, but we don't actually turn all the things on at the same time. We use the other stuff as spares in case things break, and at the very small scale they do break. And we use them for other things as well. But since 2010, in fact, the amount of additional computation that you can do on a chip has not been increasing exponentially. It's just been sort of going up in a fairly gradual linear fashion. And so this whole push to 5 nanometers, there are some companies who are saying that we actually don't need to do that. We shouldn't even do it. Because functionally the Moore's Law is already over with. But the problem is that the demand for computing is actually increasing super exponentially. We've gone from this stage where computing essentially was driven by economic growth and population growth, but now we're in an era where there are roughly 8 billion people on the planet, and practically every one of them either has or soon will have a smartphone. So they're all generating data like crazy. But the other issue is that in this thing called the Internet of Things, there are already 20 billion devices on the Internet of Things, and that is projected to grow to close to 1 trillion nodes on the Internet of Things literally by 10 years from now. All of those things will be generating data. And where is all of that data going? Well, right now it's going into data centers. But in fact, what's been found is that people are collecting data. Human beings are collectors. We're collecting data at a rate which is so high that we cannot even store it all. There's not enough production capability in the world in order to store all of that data. And so it turns out that there have been studies that say that most of the data that's ever collected in the world is only held for 3 hours, and then it's discarded. And yet that data is valuable. There's a tremendous amount of value in that, and you'd like to be able to do something with it. So this is the problem that we're running into. We have this new era, this exploding era of data that's being generated, and we have companies and organizations that would like to be able to learn from that data and generate something that's economically valuable. But that's happened at just the point in time when Moore's law essentially has come to an end. So we are at a crossroads. We're at literally a critical time right now. And for young people, this is probably absolutely fantastic, because what it means is companies and governments are spending like crazy to figure out what the next step is. Where do we go? What's the next thing? In my view, this is absolutely the most exciting time ever, well, perhaps since the discovery of the integrated circuit back in the late 1950s. This is the most exciting time to be in this field, because we're finally getting ready to do something new after 50 years of just making smaller and smaller transistors. Okay. So, there's a lot of people who have understood this for a long time, but in the United States, getting, I'll say, politicians to respond in any meaningful fashion sometimes you just have to wait for a crisis to occur. So I've actually been working for years now trying to get the U.S. government to put a program in place that would start to think about this issue seriously and start to coordinate across governmental issues and governmental agencies and companies and universities in order to help us find what the next technology is going to be. A couple of years ago in the United States, we announced the U.S. Brain Initiative. This is actually not anywhere near as comprehensive as the European initiative, because the U.S. initiative is just something that's studying the circuitry of the brain, and that's it. That's a very incredibly difficult thing to do, but at the time, it was felt that there just simply wasn't enough money to do anything more comprehensive. And so I've been working in the background, and it turns out that I submitted a proposal to the President's office earlier this year, and I proposed a new national grand challenge in computing. And interestingly enough, in October of this past year, the proposal that I had submitted was accepted, and so now there is a U.S. National Grand Challenge on future computing that's been put together. And the problem is that no good deed goes unpunished. So now I've been told, okay, go out and tell us what we need to do. Right? Okay, we have a grand challenge, but that's all it is right now. A grand challenge has been announced. There's no money and there's no program. So we have to a few little things have to be done before we're actually start doing anything. So the claim that I made, which you may not agree with, I may not agree with it fully, but it's the only thing that I could come up with, because I just don't think that quantum computing is quite here yet. The claim that I made was that although we don't really understand how a brain computes, we know some really interesting things about the brain. And we can borrow some of those things, both some of the hardware and I'll call it the algorithmic issues, and we can incorporate those into computational machines or computational engines today, and those things will actually speed up and make more efficient certain types of computation. And my belief is that as we continue to learn and borrow more and more from the brain as we understand the brain more and more, we will actually, for some significant period of time, maybe a decade, maybe 2 decades or longer, we'll be able to find a new exponential growth curve for our computation. But instead of being measured in terms of number of transistors per square unit area on a chip, the important metric is going to be the amount of computation that you can perform per unit of energy, because that's where we're stuck right now. That's what we need to be able to do. So if you're interested in any of this, here's a bunch of URLs, but you don't have to worry about this. You can just go into your favorite browser or whatever and throw in, words like computing grand challenge or rebooting computing. So it turns out that I have a large number of colleagues in the States who have kind of jumped on board and are helping me try to push this thing forward, including the IEEE and the ITRS, the International Technology Roadmap for Semiconductors, which essentially put itself out of business because we know where the end of the roadmap is, and now they've got to find another reason for existence, right? And then this is, if you go on the web, you'll find this paper here. It's a 30-page long paper. It's full of mistakes. It was thrown together very rapidly. I haven't had a chance to go through and fix all of the problems with it, but I was given a very, very short time to come up with something. So a fellow named Eric De Benedictis and I, literally threw this thing together because we just had to have something for the politicians to point to. But this describes much of what I'm going to talk about today and a lot more. But it's and I call this thing sensible machines. And the reason I called it that is I didn't want to call it sentient machines because I didn't want to scare people, and I don't really want to build a sentient machine. I want a tool, not something that's going to beat me and put me out of a job, or anybody else for that matter. So I wanted to make it sort of feel friendly and whatever, and this is the best I could do. So what's the inspiration? The inspiration is looking at the brain and understanding that there is actually a very major contradiction about the brain. The first thing is that it is incredibly power efficient. If you think about some of the computation that the brain does, for instance, a trivial one is facial recognition. Facial recognition, human beings and lots of other animals can do that with incredible speed, and given the power dissipation, you can calculate that the energy is practically nothing. Whereas if you take, say, Google, or Facebook's facial recognition algorithm, and you realize that they're running this on great big gigantic computers, they're probably requiring tens or hundreds of joules of energy to do something, and it's not very good. Right? I mean, I grow a little beard, or I turn my profile, or I age a few years, and those algorithms don't work, but human beings can do it. So the brain is remarkably power efficient, but if you actually look at what we understand about the processes that are going inside the brain, what are the state variables in the brain, and what are the primitives for computation? Well, they essentially involve ion currents and molecular concentration gradients. And when you calculate the energies of those, they're extremely high, much higher than, say, a transistor switching. And so what you've got are fundamental processes which are inefficient, energy and time inefficient, and yet you've got a system which is incredibly efficient. How and why is that? Well, nobody knows. That's interesting. That's cool, right? That's a great motivation for doing research. But I guess the thing that I'll try to point out is that what the way information is processed in a brain is via what I'll just call nonlinear dynamics. There's this nonlinear dynamical system that's continually bringing in input through multiple sensory organs. It's got some massive way of storing gigantic amounts of information, and it's able to take the incoming information in real time and essentially put it up against what's stored, and you're able to do things like facial recognition almost instantaneously. Okay. So what would the structure of a neuromorphic computing program look like? Well, in trying to help decide what a program would look like for the United States, I went to Beijing at Tsinghua University about a month ago, and they've actually had such a program running for 3 years already. It's a very, very good program. They have 35 faculty from 7 departments organized in 8 different groups. And these faculty span the gamut all the way from neurophysiology to very abstract computer architecture and literally building chips. So there's literally hundreds of students involved, hundreds of students and postdocs involved in this program. The program itself is very well conceived. It's very well led. The leadership team is superb, and it's funded to the hilt internally by Tsinghua University. So this is a receding ship already, and catching them is going to be a major challenge. They've already fabbed out 2 chips. They're brain-inspired computing chips, and they've got a 3rd one taped out already. So I mean, as I said, they're well down the road, and then they're planning to expand their program both internally within China and internationally as well. So very exciting work. That's all I can say about it. In looking at their program, I've tried to understand what a structure for a new program should look like. I have the advantage of seeing what they've done and trying to learn from that and see how I would try to structure something that might compete with that. And so at the top of the list, in terms of research, it's being able to connect the theory of computation to neuroscience. I mean, as I said, nobody really knows how the brain computes. They don't know what the computation actually is. I mean, we know that there's this stuff called spiking that's going on, but what's the computational paradigm? You look at it, in some ways it looks like it's digital, and in other ways it looks like it's analog. And it just doesn't fall into the categorization of what we normally do. There have been theories or conjectures that it's got to be Boolean, some type of Boolean computation, because neurons look like majority gates, and it could be configured to be either ands or ors. It could be Bayesian inference. All right, it could be a probability calculation. It could be, but then Bayesian inference has problems. It could be some sort of an energy minimization process that goes on, essentially like a search down a tree, a Markov chain. All of these things have been proposed. They all might be wrong, or they all might be right. The issue is that it's entirely possible that the brain is doing all of these things simultaneously in ways that we just can't even think about right now. So, of course, there's another issue, and that is just because the brain is doing something, does that mean that we want to actually try to do exactly the same thing in our computers? It may very well be that just because the brain is this thing that evolved over some very large period of time doesn't mean that it's actually the most efficient way of doing things. It's more efficient than we know how to do, but it might be the best thing for us. And so, we may decide that one of these things here, even if the brain doesn't do that, we may decide that that's the best thing that we should be doing ourselves. So that's one layer. What is the brain actually doing? Then there's another theory. Then there's another layer which is equally important, and that is, what's the theory of mind? Okay, there are literally dozens of theories of mind that have been proposed. What's the how the brain is structured? What's the architecture? What's the way in which the information independent of these different ways of computation, what's the organization of how it's all put together? And in fact, you could put together a two-dimensional matrix of the different types of computational and the different theories of mind, and you could have each of these combinations could be something that you would be interesting to pursue. Maybe 20, 30 different possibilities. So, just trying to run down all of those is rather significant. In order to do all of that, rather than be building hardware all the time, you need to have a really efficient simulation system. You need a simulator that can run computational models on systems, and you need to be able to do those computational models on a very equal footing so that you can compare them. So you understand which one is a very promising path before you start launching off and start building all sorts of hardware, because that's extremely expensive. But how are you even going to build the suite of tools and have the compact models that you need for these simulations? So that's another major issue. And then there's something that many of the other projects, I'll say, in the world that I'm familiar with have sort of neglected, and that is, how do you program such a thing? I mean, unless your goal is actually to make a sentient being and just have the thing learn and become something that just does whatever it does, in my world, I want whatever I make to be programmable. I want to be able to download an algorithm onto this thing. I want this thing to execute that algorithm and give me an answer that I can trust. All right. So how do you do that? Because in today's world, in my world, in Hewlett Packard, it turns out that at least 2/3 of all the effort that goes into building a new computer is in writing software and firmware. The hardware, that's wonderful. It's good stuff. It's important. You can't have it, but that's only 1/3 of all of the people and the money that's spent in making a new computer. 2/3 of it is in the design and in the software, and that needs to be factored in to this system from the beginning. Okay, now once you've got some ideas for what it is that you actually want to do, you need to be able to design chips. I'll call them systems on chips and accelerators. And rather than replacing the entire sort of technology that we have today, my idea is to have these things be complementary or accelerators. Essentially, put a neuromorphic type of system which accelerates a particular task on a chip. But that chip will also have many other different types of standard processors on it as well. And all of these things have to be able to talk to each other and communicate and work together. And then, you've decided on the design, but then you got to make the chip. There's the whole issue of the processing and the integration and all of that stuff. You have to have a fab where you make it. And then finally, there's devices and materials. Getting all the way down to the bottom. What are you going to do? What devices are you going to make? What materials are you going to make them from? So this is a pretty major type of thing to think about. There's a lot going on here, and so this is what I do in my spare time. Now, what do computers look like today? Computers are based upon something called the von Neumann architecture. This is what was not really invented, but at least described very well by John von Neumann in the late 1940s. And the whole idea behind this is, because of the limitations of the technology in the 1940s, they had to design computers in which there was a central processor where all of the computation was done. There was a memory, which was relatively fast, but it turns out expensive and burned a lot of power. And because the memory was so expensive, you had to have someplace else to put both data and programs. And so then there was also something called storage. All right. So this was the architecture that was put together in the 1940s because of technological limitations at the time. And 70 years later, this is still the architecture of computers that exist today. And even in the late 1940s, John von Neumann identified something that's now called the von Neumann bottleneck. And that is the fact that most of the programs and most of the data that you need for computation reside out here in storage, which is magnetic hard disk or whatever else. And somehow that information has to get into the processor during the computation. And it is this bottleneck that actually, in today's computers, uses most of the time and most of the energy in a computer. In today's computers, the processor itself, oftentimes the processors are only actually active 1% of the time because they're sitting around waiting for the data to come from storage. So what we'd like to be able to do is, first of all, combine the memory and the processing together, because that's what the brain does, and not have these things sort of distinguishable from each other. Then what we'd like to do is essentially take that unit and reproduce it, make it scalable, have a lot of it. And in fact, what you want is you want to have so much memory that in fact you don't even need storage anymore. You essentially do away with storage, and now you've got an architecture that I will call neuromorphic, in which we now have processing and memory are combined as one thing. We don't have a von Neumann bottleneck. What we have is a large number of communications channels between this system that does the computation and the outside world, so that the data bandwidth between the two is very large. So this is effectively what I'm proposing that we try to do in this computational program. Let me sort of give you a sort of an idea of how bad this von Neumann bottleneck is that we've been living with for 70 years. Processor speeds the speed of computation on a processor is about a nanosecond. So one logical step or one logic operation takes about a nanosecond on a chip. It takes about 5 nanoseconds for the processor to exchange a bit of data with the SRAM, which is on the processor itself. Most processor chips are already almost 90% memory, actually. DRAM, okay, you go off to this memory. It takes about 100 nanoseconds to get out there. If you happen to have flash in your computer system, that's a sort of an intermediate technology, but it still takes 200,000 nanoseconds to get out there. And if what you've got is hard drive, that's 10 million nanoseconds. All right? And so if most of your data is out here, and for instance, Google and Facebook and all of that, most of their data is on a hard drive. And so you can see how much time, and it turns out equivalently, how much energy is used up for in that von Neumann bottleneck. So we're working very, very hard to get rid of that thing. So the first step is to get rid of this, what we'll, looking at it in a different way, get rid of this memory hierarchy. So right now you've got this mass storage, and you're continually swapping information between mass storage and main memory, and then cache where the processors are, and then finally the processors do something with it. And so the idea is, what we're working on in Hewlett Packard Labs is something that we call the machine. And so it's a system where we're using non-volatile memory. It's memory that's not quite as fast as DRAM, but it's much faster than either flash or hard disk. It's also much, much less expensive than DRAM. And because it's non-volatile, in other words, when you put a piece of data in it, you don't need power in order to hold state in the device. So the power cost, the power dissipation in this non-volatile memory is practically nothing. So again, what I told you was that the big issue now is amount of computation per unit of energy. And so what this does is it dramatically, it may slow down some computation, but actually not most of it, not so much. But it dramatically decreases the amount of energy required for computation. All right, the next thing that we're actually working on is photonics. The issue is that instead of using copper wires in computers, we're going through and we're replacing as much of the copper wiring in computers as we can with optical waveguides, so that we can use pulses of light instead of pulses of electrons in order to communicate data throughout a computer system. Now, it turns out that this doesn't save that much in time, because pulses of electrons are already traveling at 10% of the speed of light. But what it does save tremendously is in power. Once you have the ability to do the electronic to optical and optical to electronic transitions, it turns out that the amount of power that's required to move the data around inside of a computer data center can be dropped again very substantially. So when we talk about the machine, this system in HP Labs, this is something that we're trying to actually have commercialized by late 2017. We hope to have the first working version of this computer by 2017. We might not actually sell the machine itself. We would probably host it in our own data centers and allow people to buy time on it. But it has these major components. It's got the nonvolatile memory, which is based on something called Memristors. It's got photonic interconnect. And then it's got these multi-core processors, the same type of processors that exist in cell phones, for instance. And so we're pulling together all these technologies to the point to where now this thing here, I contend, is a platform that we can use for starting to incorporate learnings from the brain into this. I mean, until we get to this point here, we could actually improve the computational part of a computer to the point to where it's absolutely instantaneous and costs no energy whatsoever, and that would barely change the capacity of a computer. So until we get to the point to where we've gotten rid of the von Neumann bottleneck, working on improving the processors actually doesn't help. But once we get to this point here, if we can sort of open up all of these communications channels, now it starts to make sense to start thinking about the processor. And so the way that's interesting. It doesn't look like that on my screen at all. Okay, well, that's the way it goes. But so another way of looking at this is that in today's world, computers are processor-centric. You've got the processor rules the world, and you've got all of these things that are peripherally outside of it, using, for instance, these system-on-chip type of systems, just sort of connected to memory. The way we're looking at this is we're moving the memory into the center, so the computer is actually built around memory and not processing. And the idea is that you send the job, you send the algorithm that you want to execute to where the memory is. You perform the computation locally with processors that are distributed through the memory, and then you just send the answer back. Okay? Rather than having to take, say, some huge amount of data and move it to some processor. So this again saves a large amount of energy. And how would this thing look on the floor? Well, what you do is you just take a bunch of components that are all the same, and you put them into a rack, and then you essentially stack them up like this. And then you can take many of these and start arranging them onto the floor of a warehouse, if you will, and have the whole thing essentially optically connected. And so this is what we actually hope to have working, up and working in HP Labs in 2 years. We've been working on this particular project for quite some time. Once we get that, the concept is that we would start customizing it. That there will be different types of computers that different types of end users will want to perform different types of computation. And so rather than trying to sell the same general purpose machine to everybody, we should be optimizing the types of computers for the different types of tasks that are being performed. And this is where I'll call it the brain processing types of ideas come in, because Here we would start introducing special purpose cores onto these system on chips, where instead of having all the cores be the same and all be some sort of general purpose processor, because you can't even run all of the processors on a chip today and won't be able to in the future, you have accelerators that do one thing and do it extremely well. And so you've got computations that are being performed, and those computations may be handed off from one accelerator to another, such that in perhaps one clock cycle, you can do something that might, with another type of system, require maybe millions of clock cycles. Maybe you can do it something like that in one clock cycle. In some sense, the idea here is to specialize and optimize every part of the system. During the peak of Moore's law, that didn't make sense, because if you tried to build something that was highly specialized, a couple of years later somebody would come along with a general purpose computer that had improved so much that people trying to do these special purpose things couldn't keep up. At the end of Moore's law, it now makes complete sense to go away from general purpose systems and start to specialize. Okay? So what are going to be in these neuromorphic special purpose cores? What types of special functions or accelerators can we create? Well, I don't know. I mean, frankly, there's a ton of things that are possible here. I'll just give you a couple examples. There are neural processes that can be emulated with devices called memristors. And I'm kind of like a big memristor guy. It's one of my favorite things. But they're, without getting into a great amount of detail, I'm just going to tell you that there are two types of memristors in general. There's one that's called nonvolatile. In other words, this is a device that will change its resistance based upon the amount of current that flowed through the device. And when you turn the power off, it remembers. It keeps that real number stored inside of it. That is the type of property that we have in synapses in brains. So I tend to call this type of device a synaptic memristor. But then there's another type of memristor which is called locally active. A locally active memristor actually has its state as a pulse. So it sends out its purpose is to create a pulse or a spike of information, if you will, and it acts as a neuron or a neuron analog in a brain. So we've got these two types of devices now. Both are fundamentally described by the same mathematics, the mathematics of the memristor, but we can do two different tasks with the different types of devices. We can build synapses in which the state is stored as a resistance, or it's essentially a real number. It's continuously variable. And there's actually many different examples of these that are already being commercialized. That are, Intel and Micron have announced their version. We've announced our version. So everyone is getting ready to start building non-volatile memories, which are essentially synaptic in their basic behavior. It turns out that the exact same material systems can be used for building these locally active or these neuronic types of systems. Where here, instead of a storage, the state is actually transmitted as a spike. It looks digital. It's based on a switching threshold, and these devices, without any transistors, actually exhibit gain, oscillations, and chaos. And those are actually, I'll claim, absolutely necessary issues for building brain-like circuits. And magically, it's the same materials, it's the same chemical compounds, if you will, as the non-volatile types, but it's a totally different physical process, totally different physics that gives rise to these two sets of properties. And I guess what I'll say is, just quickly, is that the semiconductor industry has already spent over a decade in developing these materials and has them in the fabs. So we've been working on this for a long time. We're getting ready to bring products out in the market that already use these things. So it makes it good. So anyone who's interested in this type of thing, there's a set of lectures on the web now called the Chua lectures. So all of this stuff, all of the mathematics behind these nonlinear dynamical systems was worked out by a guy named Leon Chua, a professor at UC Berkeley back in the 1960s. Most of what he wrote in that era was completely non-comprehensible to someone who's not a pure mathematician. But I've been convincing him to write tutorials, and so he's done a 12-lecture series where he's tried to bring this to the masses where you can understand it. So the viable path that we're trying to follow then is looking at these particular types of devices in order to emulate these processes that we see in the brain and perform bits of computation using these systems. So here is the first example where we've actually built this thing, and it turns out that it's exactly like the memory. So we've built a system which is based upon these Memristor devices, which is not just there to store data, but it performs a real computation. And that computation that it performs is a matrix vector dot product. So the idea here is that we have what's called a crossbar, a set of crossed wire grids where each perpendicular and vertical and horizontal wire is connected by a different memristor, and we store real numbers in each of those devices. In other words, each of those devices has a specific resistance or conductance. If we then bring in a set of voltages on the rows, that's effectively a vector. We wind up getting currents flowing out the columns that we then turn into voltages. And this thing here essentially performs the computation of a vector matrix multiplication. And it does it in one clock tick. And it does it independent of the size of the matrix in the vector in one clock tick. Now, the fact is that it's limited in its precision right now. We're getting about 5 to 6 bits precision right now. We think we can get up to about 8 bits. But there's a large number of computations for which 8-bit vector matrix multiplication is more than sufficient. And the fact that we can do this not in n squared time, but in order 1 time with very low amount of energy is sort of a major system. So this is what I mean by an accelerator. The idea behind this is we can build these vector matrix multipliers, and we can put them on a system-on-chip type of system. And whenever you need to perform, for instance, for a deep learning type of algorithm, in deep learning, roughly 80% of the computation is based upon vector matrix multiplication. And you don't need a very high precision to do it. So here you have a system that can actually do that in one clock tick every time. Okay, or you can do an instantaneous Fourier transform, one clock tick. Instead of n log n time, with a fast Fourier transform, here we can do a Fourier transform in one clock. So that's what I mean by accelerator. You've got something that takes very small amount of energy, does one thing, does it extremely well, and you can afford to put it onto a chip because you can't actually run, if you had a chip completely covered with processors, you couldn't run them all anyway. So the next issue is the fact that this guy, Leon Chua, for those of you who know anything about the Hodgkin-Huxley model of how brains create something called the the spiking that goes on in neurons in brains. What Leon showed was that the original model by Hodgkin and Huxley was not quite correct. That in fact the sodium and potassium ion channels in neurons are examples of this Memristor device. And he demonstrated, well, I guess I don't have, so he demonstrated that he could mathematically reproduce all of the behavior that people have been measuring for decades now in putting wires in rat brains and whatever else, looking at the dynamical spiking from real brains. He could mathematically reproduce all of that with this very simple model of a two Memristor circuit like that. It turns out that in my lab we understood that, and we were able to build an electronic version of the sodium and potassium ion channels. This is an example of this locally active Memristor. It's based upon a Mott transition, so the physics of the operation of this Memristor is totally different from the physics of the operation of the sodium and potassium ion channels, but mathematically it turns out to be identical in terms of how you describe it. Well, almost identical. And so we can build, and we have built, devices which will pulse with a DC bias, and the turn-on time is less than, for these very crude devices that we built, the turn-on time is less than 700 picoseconds, and the amount of energy required was less than, in this particular case, 60 femtojoules. Those are very small amounts of energy. In fact, that turns out to be 500 times faster than a biological neuron. And the amount of energy required for creating a spike is only 1% that of a biological neuron. So we have some interesting electronic devices here that if we actually knew what biological neurons were doing and we could build something similar, we would have something that's actually much faster and much more energy efficient. And in fact, we're actually gone beyond that. We now have a whole new set of devices that we've built in which we very carefully engineered them. And so we've actually improved both the speed and the energy efficiency by an order of magnitude. So now we've got something that's actually 5,000 times faster than biological neurons and only uses 0.1% of the energy. And we're now starting to build extended circuits of these in order to see if we can mimic some of the behaviors that people have reported in terms of probing rat brains. So I'm just going to go ahead and finish up here. So what I've done is I've proposed a grand challenge for the United States to put something together. And then at this point in time, I have nothing that proves that it would work, right? I've just got a couple of ideas that say that there might be something there. So it's kind of like a hard sell. But I think it's absolutely necessary. And the fact is, I don't know anything else that's any better. I mean, if quantum computing is getting to the point to where you can, actually start to do computation on exabytes of data, I'd love to know about it. But I don't think we're there yet. I don't think we're going to be there for quite some time. So I need something. And I need something that's going to work within 10 years. So I look around of all the ideas that are out there, and the only thing that I see that gives me any hope of getting on some sort of exponential growth curve is this emulation of the brain. So we need to go beyond just simple, I'll call it nanotechnology. Nanotechnology, or just building little devices, doesn't get you there. It's necessary, but not anywhere sufficient. For a complete computer, you need all of the system-level awareness. We call that architecture. We need to be able to design all of these issues. We need insights from neurophysiology, but also psychology. The psychology is the theory of the mind. You've got to have that. You need the neurophysiology to know what's the actual computations that you're doing. One of the things that we have a problem with in the commercial world is that we have to disguise any revolutionary advances that we make as evolutionary, because customers get scared if they think that they have to abandon everything that they've ever done. right? So if we came out tomorrow with a brand new computer that had brain-like computation, no one would buy it. Or maybe a couple of research labs someplace. But no one would buy it because everyone would be so afraid of it, and they'd be thinking that they've got to all of the they'd be thinking about all the programming that they'd have to do in order to make in order to be able to use it. So we need we essentially need to introduce these types of ideas gradually and literally make a new accelerator that we would use in on a chip be something that you can just call with a simple statement in a normal C-type program. Okay. And there's all sorts of fads and bandwagons that are out there where people that are just sucking way too much research funding. I mean, there's so much, graphene. Please give me a break. Deep learning. Everyone in the world seems to have jumped on these bandwagons, and so with all the money that's getting spent on that, frankly, the advances that are being made are very, very incremental. Whereas if governmental funding agencies would do the same thing as investors and understand that you don't throw all of your money on some very wild speculative investment, but you try to sort of broaden your portfolio out. I mean, that's how you actually get rich, is by having a reasoned portfolio where you spread risk and reward over a wide area. And so that's where we need this investment portfolio. And then finally, of course, multidisciplinarity is essential. I've sort of told you about all of these different levels that we're trying to bridge, all the way from neurophysiology and psychology to chip manufacturing. And the fact is that what this field or what this program will need is deep experts in each of these areas. The last thing that I want is a bunch of people who are a hectare in area and a monolayer deep. I mean, what you need are people who are extremely deep in each of these areas, but yet can actually talk to each other and explain to somebody else what it is they're doing in terms that person can understand. In my research lab at Hewlett Packard, I have a wide variety of types of people. I have literally everything from philosophers who study logic, actually, to material scientists, to chemists, electrical engineers. And what is always interesting to me is the biggest advances that we make are when two people get together and start talking about something and realize that together they can solve a problem that they could never solve by themselves. Okay? So that's where we need this multidisciplinarity in which people can communicate. Not a lot of broad but shallow neophytes. So with that, I thank you very much for your attention. And what I'd like to do is acknowledge the fact that I have a bunch of people that are working very hard while I'm standing here giving you this talk. They are writing away really hard trying to help define this program for our U.S. government. And these are the people who are part of the IEEE rebooting computing effort and the repurposed International Technology Roadmap for Semiconductors. Thanks a lot.
Thanks very much. I'm sure that we have 10-15 minutes for questions. We stimulate people.
So you mentioned one of the most important aspects of computing technology is the ability to program it, etc.
Yes.
Like, how does this square with the fact that in the machine you have to have like the custom-built hardware for certain algorithms? Like, do these things?
Well, what we're looking at is, in the second generation anyway. In the first generation, all of the processors are going to be fairly standard processors, but we plan to use many different types. In the second generation, we're looking to have these hardware accelerators that would be called by a simple statement in a software code. Okay, maybe it would be called dot product or something like that, and so once you reach that point in a piece of code, what will happen is that you will have an operation that occurs in a particular location on the chip, and then returns a simple answer. So for some of these things, for one of the types of ideas that we have in mind for the dot product engine is in neural nets. And the idea behind this is you've got a matrix of weights in the system, and those matrix of weights change very infrequently. You update them, you tweak them, you modify them just slightly, but you're doing a huge number of dot products against that thing. So, and then each dot product only takes one clock tick. So, if you actually sort of compute or ask yourself what is the potential savings in time and energy for a system that's able to perform some of these tasks in hardware versus a general purpose chip in which it's all done by using software, you can literally save a factor of 1,000 in time and a factor of 100 in energy in some of these calculations. So those are the issues that we're trying to do. Now the problem, of course, is that in deep learning, as an example, all right, so now all of a sudden we've got this ability to dramatically compress the time and energy profile of the dot products, but and that saves you 80%, but then you've still got the 20% of general purpose stuff that's not addressed by the dot product engine. So you can improve energy and speed of one particular thing by orders of magnitude, but that only improves the overall performance of the system by a factor of 5, right? But that's still a pretty important thing to do. And then you just have to say, all right, well now what's the next thing that we can apply to this thing that still is taking 20% of the time? And what are there things that we can accelerate in that in hardware as well? And so that's kind of like the chasing our tail type of thing that we're going to have to do. It turns out that one of the things that we're looking at is just better A to D and D to A converters. That's a technology that's been around for a long time, but it dominates the energy and time profile of our dot product engine. So we think that we can improve that by maybe even another order of magnitude by a better choice there. So there's, we're at a stage right now where we're just going to have to sort of squeeze out every little thing that we can find, and you squeeze out one thing, and what it does is it takes the bottleneck from one place to another. So you don't, I throw these numbers around where you can improve one particular thing by a lot, but for a complete algorithm, it's significant, but not gigantic, and that just means that I can see generation after generation of new hardware coming out that's where things are specialized for performing specific tasks.
Sorry, you mentioned chaos as one of the sources, nonlinear dynamics is one of the sources of computation. I presume that runaway solutions don't worry you. How do you
well, it depends upon the certain types of computation. Now, it's not necessarily the fact that you want to. There are some computations for which you would actually want to have chaos, but in fact, one of the things that Leon Chua has shown is that in brains, in biological brains, neurons are what he calls poised on the edge of chaos. You can sort of think of that as saying that neurons in the brain are right on the edge, okay? And what that means is that when it's poised on the edge of chaos, it's stable, but almost any perturbation can cause it to go chaotic. What that actually means is that when a pulse comes in that's just large enough to sort of move this thing out, it will fire very rapidly. So being capable of chaos actually gives the system or puts it as close as you can get to, I'll call it optimal efficiency in the system. And so you don't always want the system to be chaotic. However, it turns out that, at least I believe, and some other neurophysiologists that I've talked to believe, that the fact that neurons in brains are on the edge of chaos is actually critically important to our mental health. The issue being that if with this nonlinear dynamical system, if it weren't for the fact that we had some pseudo-random firing of our neurons going on all the time, our brains would just simply synchronize. All the neurons would synchronize and would just turn into a harmonic oscillator. The word for that, that's an epileptic fit. All right, and there are examples of organisms which do that. They're flatworms. All they have to do is this, right? But us, we need something to break the synchrony in our neural circuitry, and so it's very likely that these pseudo-random events, which are caused by the sort of the chaotic capability of the neurons, are the things that essentially break the synchrony in the brain circuitry, preventing us from just turning into flatworms. Now, I have another wild theory, and that is that these same random firing events can actually create connections between different parts of the brain that wouldn't normally be connected. Because, in a brain, in a life experience, you have a sequence of events that occur in time, and those get stored away in various parts of the brain. When a human being has an aha moment, a realization of something, how does that happen? I mean, what if you have one piece of knowledge that's stored away in your brain over here, and another piece of knowledge that's stored away in your brain over here, and effectively there is no logical path that you can follow in a Turing type of process that would get you from this state to that state? Well, if you have random events that are firing, every once in a while you might have a random event that connects two pieces of the brain that would not be logically connected in any other way. And it's those types of random events that may very well give rise to intuition, that give you the aha moment. These two things are related to each other. And the way in which you did it was through, I'll call it this random event or pseudo-random event, rather than sort of following down some sort of a tree and going all through all of the pathways of the tree. Now that's just a wild, a wild idea of mine, but it's something that I think is worth exploring.
Any other questions? You mentioned this Chinese initiative. That they have made some chips.
Yes.
Could you maybe elaborate a bit more on what they've done?
Okay. Well, they're being a little bit secretive about it. The name of the chip is Tianjin. I'm pronouncing that terribly, but my staff tells me that translates roughly as something like divine entity. So they are not being bashful about their ambitions for this thing. It's intended to be used in robots, for effectively sentient robots. That's the application that they're looking at. The first chip is, I can tell you several things about it. It's based upon spiking. So they're using spiking networks, and the computation they're performing is actually Bayesian inference. So what they're doing is they're sampling the spiking frequency in a system to compute a probability in a Bayesian inference. And then they actually have a process which they call sleep, in which they go through and they normalize the probabilities in order to be able to then calculate the final probability event. Their very first chip and they call it Tianjin 0.6, so they don't think they've gotten to 1.0. Their first chip is all CMOS, manufactured at 110 nanometers, using a foundry in Taiwan. Tianjin 0.7 uses a Memristor crossbar as the memory. So they're replacing SRAM with a Memristor crossbar, and that, at least on paper, dramatically improves the amount of memory that they can integrate onto the chip, because SRAM is gigantic and Memristor memory is very, very compact, and should dramatically improve the power efficiency as well. And then, which kind of the thing that kind of got me and got my attention is that Tianjin 0.8, which is the one that's just been taped out, is supposed to use a dot product engine for a lot of the computation that they're going to be doing on board the system. So that certainly got my attention there. Let's see, any other random issues about it? At least for the first several generations, Tianjin 0.6 to 0.8, they're going to be doing all of the training, all of the learning off the chip. No, actually, for 0.7, all the learning is off the chip. For 0.8, they're planning to do the learning on chip. So, it's a very, very well thought out. They're on a cadence to produce one new chip every year, and the idea is they're just going to try something. Just build it, experiment on it, learn as much as they can, take whatever they've learned, and then that learning essentially goes into the N+2 chip, and into the design of that. And then they're just going to sort of roll it, and at one new chip every year, and then you'll just drive down the technology nodes, starting at 110. They'll probably I think their next one's probably at like 90, and so they'll just sort of go ride down the technology nodes. By the time they get to Tianjin 1.0, they think they're going to have something that's going to be pretty spectacular, and I think that's probably the case, and that would be due in 2 years.
Another question based on this was making chips like that is very costly. So, is there any way to try to bring this kind of exploratory research on these new computations in such a way that the cost is sufficiently low that the mundane academic laboratory or group can also tackle this?
Well, if you write to them, they'll probably send you their chips for free.
Yeah, but that's not the same thing as playing around, making your own design.
That's exactly right, but that's what they're trying to do. They're trying to get everyone else dependent upon them for actually making the things. Very clever. I mean, they have a very clever business model. Let's put it that way. And you're right. It's a problem. And I mean, even for the United States government, I'm trying to convince the U.S. government that the U.S. government needs to have a real foundry. We don't have one in the United States. We don't have a governmental foundry. There are places in Europe. I mean, you've got IMEC. I mean, something like this can be done at IMEC, for instance. And as a professor, you can collaborate with IMEC, and if you get enough people sort of involved and engaged, you could do all of the foundry processing through IMEC. That's a unique opportunity that Europe has, and something similar could be done, not quite at the same level, but you could do something similar in Leti. In the United States, we actually don't have that infrastructure. I'm having to try to figure out how to convince other U.S. governmental agencies to either take existing facilities and improve them and bring them up to speed, or even bite the bullet and invest significant amounts of money in building something new. But that's a pretty hard sell. I mean, we're talking, an absolute state-of-the-art foundry right now at 14 nanometers is it's about $10 billion. So it's, I mean, the buy-in is huge. Europe has a big advantage because of IMEC. Tsinghua University plans on building its own fabs. They've got enough money to do it.
So because of its continuous nature of those this type of different computing ways of computing, how does it affect with error correction and this?
Well, I mean that's a great question, and the fact is that one of the things that is known about brains is that there's these random pulses that are going off. There's failures. There's neurons that are dying. And then there's new connections that are being made. That's something that's actually very difficult to, that reconfigurability is somewhat difficult to emulate in a hardware system. And so that would require almost certainly a significant amount of clever software, running on a piece of hardware. So you wouldn't be able to, within any reasonable time frame, we're not going to be able to emulate all of the functions that go on in the brain, for instance, just in hardware. So there's going to be some combination of hardware and software in order to be able to deal with defects and faults and just random stuff happening. But in some of those cases, the random stuff might actually be some of the more interesting part of what's going on.
Forgot my question. No, it's about memory.
Yes?
So something that was almost touched on was so in the training process.
Mm-hmm.
You mentioned the training could take place in different places. And I guess my question is two parts. First of all, how does the training time factor in? Is that something that's relevant? Because, for example, now I've spent about an hour learning to recognize the face. I could probably do it very quickly, but that costs an hour of time for training. And then the second part of the question is, so I don't have a very good memory. Maybe in 10 minutes I'll have forgotten your face. But is this memory loss something which is necessary because I'm processing so much information all of the time that obviously I prioritize, but maybe how does the memory loss affect me as well?
Well, I mean, you point up some interesting questions, both about how the brain actually works and how something like this would happen in a machine. Forgetting actually for brains is very important. What brains are able to do is they're able to abstract and categorize, those are critical because if you tried to store very, very high fidelity data about something, it could take forever to sort of run through it all. Whereas the brain has this remarkable ability to have very high level sort of abstractions that it's able to go to very quickly and find those. And then, maybe there's something else around there that helps you just fill in the details. And whether you do that through memory or you actually recompute based upon some set of basis vectors that you've got is unknown. The same thing would apply for one of these computational systems. But here, I mean, literally one of the things that we're seriously considering is a machine with a memory that's so large that it remembers everything. That every piece of data that you bring into it stays there, or at least say for 10 years. And but then the challenge is if you've got exabytes of data in your memory, again, how do you find something with all of that data? Which that means is that you've got to be continually processing that data at some level. You need to be abstracting it. You need to have metadata, or you need to have some ways of helping you reach the point to where this data is to help you to deal with it. And that's this gets back to sleep. This is one of the things that people think in real brains, and there's a guy named Sen Song who's working on the Chinese brain-inspired computing project. He believes that sleep is actually essential for these reasons. It's the time when the brain actually can reorganize the input. So you had a bunch of input during the day, and it's just coming in. It gets streamed into some place, but then you've got all of this other data that's been there for decades, in my case. And then how do you reorganize that? And so that's one of the aspects of sleep. And for a brain-like computer, or a computer that has very, very large amounts of data, it may very well be that the computer is continually running or has, almost called like a subconscious, where you're continually having to be organizing and reorganizing and tagging in the background, such that when you actually have a query and you need to do something, you're sort of optimally configured to be able to do that. But that type of process actually still can be much more efficient than trying to sort through some huge amount of data that's just been sort of splatted sequentially in time into something. But that is a major issue, and we actually think that in some of these computers, most of the computation will be just done as background, waiting for a query that may never arrive. That you store this data, and the probability that any particular piece of data is actually accessed may be a small fraction of a percentage. That in fact most of the data that you bring in and put there is never used, but it's there if you need it. And in order to be able to do that, you need to have a storage medium that's ridiculously inexpensive. It has to be really cheap, and it can't actually use any power. It can't be burning any energy while it's holding that data there. But then when you do need it, or if you do need it, you need to be able to access it effectively, instantaneously. So that's a very, very interesting challenge.
Is there still room in fundamental physics fields that to optimize using a model that we can expect? For example, maybe a new type of transition, metal insulators transition.
Okay, so you ask a very interesting question. This whole issue of switching, we are presently looking at Mott transitions, but having, I'll call it a first-order phase transition, which, in our case, it's actually thermally driven. And you might think, oh, thermoelectrics, that's crazy. How can that possibly be energy efficient? Well, at the nanometer scale, it turns out that the heat capacity of an element is very, very small. So it doesn't take a lot of energy to make a significant temperature change. But it might be better to have something that will undergo a phase change, say in a field, or something like that. So I think that there's a gigantic amount of, I'll call it material science and physics in the realm of phase transitions is at one level. And then there's a whole bunch of work in the whole area of understanding chaos in material systems. This is something that was very popular back in the 1980s, and there were books written about how chaos was going to sort of be this great wonderful thing, and then what happened is it got hard, and after it got hard, people stopped doing it and went off to try to find easier things to do. In order to tackle some of these problems, we're going to have to stop jumping on the next best bandwagon. Instead of, graphene, one of my favorite things, right? People all over the world are doing totally shit experiments on absolutely crap material, and are getting papers published in Nature and Science because it's the thing du jour. It's easy to do. It's not hard, right? Anybody can go out and go, and publish a paper, right? And I guarantee you that 90% of it is wrong, and probably another 9% of it is immaterial. Now, all that said, there's a small core of very, very excellent science there. So I'm not going to say that it's all bad. But the problem is that there are way too many people doing it, because the other things, things like Mott transitions, various, the whole field of chaos, they all got hard. They all got really hard, and people were just challenged. It was hard to do an experiment. It was hard to get a result. It was hard to get anything published. And so they went off and looked for something easy to do. And we got to stop doing that. You know, as a scientific community and the funders of science have to just stop this whole bandwagon thing where you just jump on the next easy thing to do and just confront the real problems and get to a point where you know, you're actually making significant progress. You know, what I tell people, you know, I'm in an industrial laboratory, and people say, oh, well, I'm working on real hard problems, you know, I'm doing this, I'm doing that. And I said, look, when the research is done is when the work begins. Development, I guarantee you, I've been through this now, development is 10 times as hard as research. No matter how hard you think a research problem is, if you're going to take the results of that research problem and give them to somebody who then has to develop it into something that's useful, you're going to wind up spending 10 times as much money, you're going to have 10 times as many people working on it, and it's hard. And then, once you get to the end, to the development stage, now you've got to take it to commercialization. Now you have to get it manufactured. That's 10 times harder than that. And so the amount of money spent then goes up by another factor of 10. All right, so if you think you spent something like, I don't know, $10 million on a research program, it's going to cost $100 million to do the development and $1 billion to get it to the point where it's commercialized. And each time, the number of people and the amount of effort actually goes up. So the research is the easy part. You know, been through this now. That's the easy part. You don't even really start sweating blood until you start doing the development. And most researchers will be thankful if you never actually see that, because it's not pretty. But that's just really, you know, the way life is. And it's one of the reasons, you know, it was mentioned about my talk that I gave in Helsinki a long time ago. I worked backwards down the chain. I said, okay, if you're willing to spend this much money on manufacturing, okay, if that's your budget for manufacturing, what can you afford to do in development? If that's how much money that you can afford to do the development, how much research can you actually afford to do? I mean, if you spend so much on research and you develop all of these possibilities, you can't even afford to do the development on it, let alone the commercialization. So even in a very large company like Hewlett Packard, we can maybe afford one project a year going into commercialization. That means that maybe we'll have 2 or 3 in development, and that kind of limits how many you know, the amount of research projects that we can have. So it sort of cascades downwards, and it's one of the reasons why, you know, governments have to be supporting research in this area, because you go backwards through the chain, and it's very, very easy for managers and in companies to decide that we shouldn't be spending any money on research at all. So that's you know.
Be very brief, because the boss is
Okay.
me. But we've got one last quick question before we go and have a buffet dinner. So if you can suppress all of the other exciting questions, Stan will be around to query him privately as well. But maybe one quick one.
Do you still expect the theoretical physics can improve this industry?
Oh, absolutely. I mean, you know, as I said, the whole area of chaos is chaotic. I mean, the types of things that have been done, I mean, you know, it's the case. All the easy stuff's been done. You know, most of the work on chaos is on trivial models. You know, it's all you know, no contributions or no thinking about bandwidth limitations or noise in the system or all of this stuff. I mean, I mentioned this earlier. I mean, experimentally, we do all of these measurements, and I can't tell if a system is chaotic or random. I can't, experimentally. You know, all the tests that people have, that, you know, Poincare plots, Lyapunov exponents, all of these things, they blow up, or they just dissolve in the presence of experimental limitations in terms of measurement and being able to do an analysis. I mean, we just really got to have I'll just say a better theoretical foundation in this whole area of chaos. It's as I said, you know, It was the big thing back in the 80s, and then when all the easy things had been done, people walked away from it.
But it's a positive note, actually. So there are jobs to have there for theoretical physicists as well.
Yeah.
I suggest we thank both Serge and Stan for great